A lever is used to move a large rock by placing it against a smaller rock. If the smaller rock acts as a fulcrum, that is 15 centimeters from one end of the lever and 85 centimeters from the end where a person applies a force, what is the mechanical advantage? So I've already drawn a picture of this situation when we were discussing simple machines and mechanical advantage on the key concepts slide. In this problem, though, I've been given some numbers, so I think there's kind of like that 85 centimeters I might put into this picture and say, oops, that's really representing the distance from where this small rock acts as a fulcrum to the lever to where I'm applying an input force, and then, I don't know, somewhere in here, right, is the 15 centimeters. So maybe that can help me answer this question about mechanical advantage by doing some kind of analysis of those forces. What I'd like to do is draw an extended free body diagram, and I think for make it easier to look at, I'm going to take this lever and make it horizontal, and then I have that force Fn applied at one end, right? So this is Fn. Now, there's a subtlety here because in this picture I said, well, the output force is applied to the rock in this direction, right? I apply this force to the lever. But if I'm drawing an extended free body diagram, I should only be looking at forces applied to the lever. So really by Newton's third law, the rock applies a force back on the lever. So I'm going to draw F out, or maybe it's paired Newton's third law force, but I'll still label it as F out here, but pointing down towards the lever. Just because I want to make sure that I'm consistent about what system I'm using. And then the fulcrum is going to apply some, I'm going to have to go over here into the picture, but some larger force. It has to balance out these other two forces, so its length should actually be equal to the sum of the two lengths of these. I might be a little short on that here. So let me now, in this extended free body diagram, I'm going to use this as my origin for determining torques because I think that's going to be simplest, and that's kind of like how we looked at a seesaw, right? So maybe I could just say, hey, we're going to do the seesaw equation, and then recognize we have, you could say lever arms. We usually say moment arms, but it's sometimes also said lever arms, and if you think about it, that makes sense given that we're talking about a lever, right? But moment arm, lever arms, almost the same thing actually. Pretty much is the same thing. And those are 85 centimeters and 15 centimeters respectively for these forces. And one version of the seesaw equation, we've seen we had I think M1 R1 is equal to M2 R2, but you could also say in terms of forces, maybe I could write this I would want to say maybe R1 F1 equals R2 F2 is like a seesaw equation. It's basically saying torque on one side of the seesaw is equal to torque on the other side of the seesaw, provided that it is in balance. So when I've said that we look at a lever kind of quasi-statically, right? The goal, of course, is to move this big boulder, but it's going to happen really slowly. But I'm basically looking at torque balance, which it corresponds to what we said was for a static system in equilibrium. So when we say quasi-static, we're basically saying, well, we're recognizing it's actually going to move, but we're going to pretend that it doesn't when we're doing the analysis, right? But again, this can also be thought of as torque in and torque out. And in that sense, you can maybe think of it as it's the lever arm for the input force and lever arm for the output with the output force respectively on either side. And since my goal is to find the mechanical advantage, I'm just going to abbreviate that with MA here, right? Which is equal to F out over F in. But with this equation here, I could cross multiply. In other words, I could divide both sides by F in and by R out. Then on the right, I would have F out over F in. On the left, I would have R in over R out. I'm going to swap the sides on that, though, and make that the right side of what I've got here. So R in over R out. And again, this is algebraically equivalent to what I had up there. But R in is really this 85 centimeters, and R out is the 15 centimeters. So this would be equal to 85 centimeters divided by 15 centimeters. I'm not going to bother to write the centimeters because I know that those cancel out, and the mechanical advantage should be a pure number. It doesn't have units. And when I go into my calculator to find out what 85 over 15 is, it's like 5.666 repeating, so it's presumably equal to 5 and 2/3 as a mixed number. But maybe in this case, since we're in a science class and we do sig figs and rounding and stuff like that, we will report 5.67 for this mechanical advantage. Let's go ahead and check if that is the correct result, and it looks like it is.